Good evening, everyone. Welcome to Social Computing course. Right? Hope everyone is doing well. Right. Well, we'll be starting soon. Last week we looked at some fundamentals on graph theory, so we will continue those, and then we'll wrap graph theory up tonight. And also we will see our first assignment, which is entirely on this topic. All right. Before I start, I want to know if you guys have any questions about the topic that we had discussed last time and tonight, the graph theory. If you have any questions, let me know. Okay. All right. So last class, we started looking at different types of concepts and definitions for graph theory, um, types of graphs. We also looked at graph representations and data structures, and then started looking into the relevant concepts of graph theory and social network analysis. Right. And I believe that's where we had stopped. We had looked at some forms of clusterings, community extraction from graph theory point of view on social networks. So I believe this was the example that we had taken and shown how one of the forms of clustering called spectral clustering can help you identify various communities in a graph, showing how reduction from this high dimensional space to a lower dimension space can then allow you to run very straightforward supervised or unsupervised machine learning algorithms like k-means to arrive at these clustering configurations, right? So this is what we had discussed last time. And this class onwards, we will dive a little bit deeper into more social science um, aware concepts or more social science relevant concepts in social network analysis that also leverage graph theory and its applications in social media platforms, right? So some of these concepts such as triadic closure mean when two people have common friends, then they're more likely to be friends in future. It's something that you may have already noticed on Facebook when you start befriending folks. Facebook algorithms also recommend you some new friends, which may be common or shared friends with the people that you friends with. So these type of concepts are quite prevalent in social networks also. So social media platforms take advantage of such concepts. This is an example where you can notice that how B and C that have common friends like A are also suggested to be friends with this thick black edge, right? So these and plenty of other examples exist where social media platforms like Facebook or Twitter X, they use these concepts. Another concept is clustering coefficient, which is also quite prevalent in social networks, and you may have noticed this yourself within your own local networks or private networks, where you see how your friends are connected to each other or probably not. Then you will notice that there are some individuals in your network who everyone follows, but perhaps there are no connections in the followers or among the followers. So those type of networks are considered to be as non-cohesive clusters or non-cohesive networks where the friends of a person are not following each other. So those type of networks also resemble more like a star-shaped network where there is a single popular node in the network and others are simply following them without knowing the other followers of that person. So there is a concept called clustering coefficient that measures how clustered your network is, meaning how well your followers or your friends know each other or are connected with each other. And the way to measure that is you look at the number of closed triads and the ratio with a number of possible triads. So if you look at these examples, the three networks on the slide, you can see that for the blue node on the left has three friends. So you can see that the blue node is connected to all these three friends, all these three nodes. But the three nodes or the three friends of blue node are also connected with each other, right? So in this case, the clustering coefficient of the blue node is 1, meaning there are three possible connections among the friends, and all those three are existing, or they all exist in the network. So this also shows that this is a completely connected network, right? Which further in social networking or social media environments mean that there is good amount of information transparency in this cluster. So everyone knows everyone else. So there is very little relationship fatigue, meaning you are not hiding things from the others, or you're not filtering information that is passed to you from one of your friends to the other friends, right? Which usually happens in cases where such triadic closures or such connections are not maintained. So if you take a look at the second example, where the blue node again has the same three friends, but those three friends are not connected with each other. So imagine that the red links are the ones that have been deleted from the previous or this earlier case. In that case, you can see that only two friends know each other, but the third friend does not know about the other two friends, right? Or they are not, he's or she's not connected with these two individuals. In this case, you may realize that any information that is passed to the blue node from these two friends may not be shared with this third friend directly. So that information has to go through the blue node. Now it becomes the responsibility of blue node to make sure that the information is either fully passed or filtered, passed, selectively passed. So that incurs something called relationship fatigue. All right. So you have that psychological effect on that blue node. In the third case, which is even worse, where none of the friends of the blue node know each other, right? So imagine that all those three links or three connections that existed in graph one have been deleted. So only these individuals know the blue node, but they don't know each other, right? So now it becomes even greater responsibility of blue node to share the information appropriately, right? So that is another case. So when we look at the clustering coefficient for the first scenario, it is 1, which means information transparency. There is a full information transparency, at least in terms of the structure. So everyone knows everyone, so information is flowing freely. But when you look at the second example, only one relationship is maintained with the possibility of three others, or three total relationships. So in this case, the clustering coefficient is 1 over 3. But when you look at the last example, where none of these edges are connected, then the clustering coefficient will be 0. Right? So there are three possible triads, but only, or none of them are connected. So that means 0 over 3, clustering coefficient is 0. All right. Now, there are multiple reasons for such type of triadic closures where, let's say, if two individuals B and C are not friends, but they have a lot of common friends, then they have more opportunities to meet or more opportunities to run into each other. Hence, they are more likely to be friends in future. Another way of thinking about this is B and C both trust their common friends. So they may have a higher perception of trust for each other as compared to a random or a stranger. So that is also another way of thinking that these two individuals, B and C, would become friends in future, or highly likely to become friends. A also has an incentive to bring B and C closer. Otherwise, there could be some stress on A Again, that goes back to the point where if A's friends are not connected to each other, then A has to be the broker of information between B and C. So they may have to selectively share or make sure the information is fully shared. So it just adds a little bit of stress on A. So A also has an incentive to bring B and C closer. Hence, these triadic closure properties are very well maintained in social networks. And that's also one of the reasons for these social networks to have these local cliquish properties. So globally, when you look at the entire social network, you will find that there are so many cases where an individual may not know every other individual, but locally, when you start looking at a macro or sort of micro level in that social networks, then you will see that people know each other, or there are these cliques, which could emerge as people working in the same workplace, or they are students, or they are taking same courses together, they enroll in the same degree program, or they have same interests. Maybe they're part of a book club or other types of activities, co-curricular activities, and that's those are the things that are bringing them together, right? So such type of small cliques or local cliques are properties of social networks. In fact, for the third point, there is an interesting article that has investigated this even further and found an interesting, striking correlation between people who have open triads and their degree or propensity to contemplate suicide. So a higher correlation was found between people who have open triads, meaning their friends are not connected to each other, and their suicide ideation probabilities, right? And this study was conducted among adolescents, so people who tend to be a little bit more on social media platforms and such. Okay. Now we have looked at a lot of various concepts on social networks. Now, what distinguishes social network from other type of, let's say, random networks or lattice cell-based networks are these power law or degree distributions, right? And this is a very famous phenomena, which I'm sure many of you have read about or seen this, which is very common and existent in day-to-day lives, which is called the long tail phenomena. Um, Meaning the 80-20 rule, or in social networks context, then you will see there are more people who are less connected than some people who are very widely or very popular connected, right? So those are sort of the short heads, and the people who are very sparsely connected are in the long tail. This nature of or this structure of the networks is quite prevalent in any type of social media platform. So if you look at websites, blog sites, Facebook, Twitter, Instagram, you will find that only few people are that celebrity status social media influencers, and majority of social media users are not that highly connected. So that basically is a phenomena that has been also conceptualized mathematically using this power law degree equation, right, which is provided here. So fx equals ax to the power minus beta, and these coefficients a and beta govern how skewed the distributions of such power law networks look like, right? So in fact, if you do this experiment on social networks where you collect users and their followers and build that chart, you will see exactly a long tail phenomena. But if you do a log transformation of those data points, then you will see that this linear behavior exists. Meaning, if you look at number of connections or degree of an individual, and how many such individuals are there with that much degree, then you will see such behaviors. right? And for example, in this case, we are looking at Twitter on the second trend chart. You can see that on the x-axis, we have out degree, meaning how many people you follow. And then the frequency on the y-axis shows how many such individuals exist. So for how many people with degree 1, how many people with degree 10 or 100, 1,000, 10,000, and so on. So again, this is a log scale. Similarly, for frequency, you can see number of individuals in 1, 10, 100, 1,000, and 10,000. So this shows how many people with only one follower is a lot. And then as you go further with the number of out degree, then you'll see that this drops drastically. Even though it's a linear fall, but since this is a log scale, this is, if you retransform it back to the original scale, the linear scale, then you will see that this will be an exponential drop, right? So that exponential drop is exactly like what you see in the long tail phenomena, right? And this is common throughout all social networks. You take example of Twitter, Instagram, TikTok, Facebook, YouTube. Not every video reaches virality. There are few videos that are seen massively or massive followings of channels, but majority of channels have a handful or sometimes even single digit subscribers or followers. So this long tail phenomena is very popular in social networks. And in fact, this characteristic is so widely used that in case you don't have access to social networks data, social media data, you can use these equations to simulate social networks. And that's what we are going to discuss in the next slide, but that's also where we are heading. So in case once we study these properties of social networks, then we can simulate our own social networks, right? All right. So such networks are also called scale-free networks. So it doesn't matter how big or small the network is, the phenomena still exist, that power law distribution still exists, unlike random network, where you will say everything is uniformly distributed, the number of connections are almost equally likely, which is not true. In real world setting, you are more likely to connect to people who you know, or you know someone who knows them, but not just complete random strangers, right? Hence, this property of scale-free network exists in social networks and social media platforms too. Um, the way we connect with others also follow something called preferential attachment. So we want to connect with those who we know or who already have a lot of connections. So we try to follow, let's say, opinion leaders or experts in certain topics, right? So that also transforms to rich and richer, rich get richer effect. So when you look at social media platforms, let's say Facebook or Twitter, you'll see that some individuals who already have a lot of connections keep getting more and more followers as opposed to the others. So that's exactly what is preferential attachment model. And these equations govern those behaviors where the probability of creating an edge between two nodes I and j actually depends on the degree of the destination vertex I, right? Similarly, in a directed graph, if the edge is from j to I, then if j is trying to connect to an individual I, then j is choosing an extremely popular individual. So the probability of this edge depends on what is the in degree of that vertex I, right? So the higher the number of connections for that individual I, the more chances are that any individual like J would try to connect to them, right? So we observe two types of properties here. One is we want to connect to individuals who we know or we have shared connections with, right? Through the clustering coefficient or triadic closure property. The other is preferential attachment model. And both these phenomena exist in social networks, which actually give us this kind of a dichotomy in the social networks, this view where um, Locally, you will see highly clustered communities, highly cliquish communities, but globally, you will find such star-shaped networks where single individual has a lot of followers, but most of the people have very few following, right? So these two behavioral properties of individuals of our societies lead to such type of structures in social networks, right? Any questions so far? Okay. All right. So we looked at this just to summarize clustering coefficient. We looked at clustering coefficient, which is a characteristic property of a node, not a network. So it's a node level property, just like we saw centrality, right? Which is for each node, degree centrality, betweenness, closeness, eigenvector, and so on. Cliquishness is for your network, right? And social networks have larger clustering coefficient values as compared to random networks, just because the fact that we try to connect to people who we know or who we have shared connections with, as opposed to a random network where you're just randomly connecting with others. So that's why clustering coefficient values on average are higher in a social network than a random network. Okay. All right. Now, we have been looking at social network analysis from mainly computational standpoint, or how computer and information scientists look at social networks, people like us. But in social sciences, or rather social scientists, have been looking at social networks even much before then internet existed, let alone Facebook and Twitter came along. So how did they analyze such social networks, which came from real world observations? Of course, they were not looking at internet connections or this and that. So often these were connections based on telephone conversations, person A calling person B, or a group of individuals hopping on a conference call type of a link, where you have multiple individuals talking to each other on a phone. So those type of connections, plus physical connections, real world connections, were being analyzed by social scientists much earlier, much before then internet came along. And one of the experiments that we saw was 6 degrees of separation, which famously concluded that any two individuals randomly selected are no more than 6 hops away. And that was also conducted using mailing postcards and such, right? So no online networks were there at that time. So social scientists used something called a sociogram to define all these concepts. A sociogram is nothing but a modern day social network, where you have actors, which are kind of nodes in our social networks, but they were considered as points or dots in a sociogram that can make choices, and these choices were relationships, right? So actors that choose each other, meaning they're making mutual choices of establishing relationships with each other. They were creating something called undirected graph. So something that we have seen also in our earlier concepts, when mutual relationships are there, then you don't have directions on the edges. These are undirected graphs. But if the actors are allowed to make one-way choices in the sociogram, then it is the same as directed graph, right, where choices are not reciprocated. And in a modern day setting, Twitter is a great example where, or X is a great example where individuals can follow other individuals, but not necessarily they will get a follow back, right? One common concept that also exists between sociogram and social networks is cliques, where a group of individuals all connect with each other or all choose each other. So that's the same concept. So even the social scientists call them cliques as we call them, right? Okay. Now to study an individual's network, social scientists or in sociometry, there is a special term which is ego alter network. Right? This is something that we haven't discussed, but we have seen glimpses of it just now, a few slides ago. So we'll go back there and then we'll see what ego alter network is. But conceptually, ego alter network is defined as a network of friends that connect with you. So if you have a set of friends, then you're considered as the ego of the network, and all your friends are considered as alters, right? This is something similar to what we saw when we looked at clustering coefficient, right? We were looking at an individual and their friends, right? So ego and alters. So again, the idea would be how well connected those alters are, right? So the clustering coefficient would be defined for ego for a person, for let's say you, if you're trying to analyze your friends, how well connected they are. So then you will talk in that sense, right? So it's an ego alter network, and your alters are either very well connected or poorly connected. Right? Okay. Now, how did the social scientists define sociogram? And this is where you will find a quite striking similarity with our adjacency matrix. Now, if you look at this example of four individuals, red dots, so one connects with four, or one chooses four, since there are no arrows here or no directions, then you can consider this is an undirected network. So basically 1 and 4 choose each other, 2 and 4 also choose each other, 3 and 4 do the same. When you look at the sociogram here, this is nothing but our adjacency matrix now. So each row corresponds to the vertex or the individuals. Similarly, each column corresponds to the users or individuals. So we can consider the first column as individual 1, 2, 3, and 4, and then the rows, same thing. Row 1 as individual 1, 2, 3, and 4. And when you look at these cells, individual entries in the sociogram, then you will see that for the last row, for instance, which is your individual 4 connects with individual 1. So there is a 1 here. Individual 4 also connects with individual 3. Individual 4 connects with individual 2. And since it is an undirected graph, you will find that it's a symmetric matrix. So same relationship exists on the column as they did on the rows, right? So this is again very similar to what we call as adjacency matrix, but social scientists call them as sociogram. Now it is important to know the vernacular that is used in different disciplines, especially since social computing is such an interdisciplinary topic. Often you will find if you're doing research that you will collaborate with scientists or researchers from different disciplines, maybe more particularly from social science discipline, then we understand our languages, right? So if they're referring to sociogram, we know what that means. That is a adjacency matrix. All right. So I'll leave you guys to look at these other two examples and see how the adjacency matrix or the sociogram is constructed, but follows the same principle as we looked at for the first example. So if you get a chance after the lecture or some other time, you can take a look at these two other examples. Okay. All right. Now we will switch gears and start looking at something um, quite an interesting property of networks. Now, if you remember, towards the very beginning when we started this lecture, we talked about two things, network structure and network behavior. So far, we have been discussing about mainly the network structure, but how does a network influence our behaviors? Right. I'm sure you may have seen that in your own social network sometimes, that you get influenced by someone's behavior or someone's choices, or someone gets influenced by your behavior, your choices. You buy something, and maybe a few days later or a few weeks later, you see that the other person, your friend, has also bought the same product or a similar product, right? And this buying decision, this influence does not just get restrict to buying decision, information discovery. So the type of news outlets you read, the type of news sources you consume, um, those could also be influenced. But in fact, there are several other virtues that that spread in a network, so to speak. So your behaviors in terms of happiness, sadness can also influence your neighbors or your friends' behaviors in terms of the same virtue of happiness, sadness. In fact, this is stretched into other virtues like smoking cessation. So how people influence smoking behaviors in their friends, obesity, and many other such virtues. I believe towards the end I have a slide. Yeah, you can take a look at some of these links, and you can download these studies and take a look at what these studies have reported. But I will take one example, which is spreading or spread of happiness on networks, and see what this actually means and what type of experiments were conducted and what conclusions were obtained during these studies. Right. So how networks influence our behaviors. So this is a study that was conducted by a social scientist and a medical doctor who looked at various patients as they arrived at the hospital, and the data that was recorded was strictly survey based, and the participants were asked if they accompanied the patient, what is the relationship with the patient, and how they feel in terms of a scale of sadness to happiness, almost like a Likert scale between 1 through 5 scores, one being probably sad and then 5 being happy and so on, right? So such a data was collected through surveys over a course of 5 years, and for the first year 1996, so again this goes way back, right, almost 30 years back. Here you can see how the network looked like of people who know each other as they were accompanying the patients or other people in the hospital they knew. And 5 years later, in 2000, they built a similar network. And of course, you can see that 1996 network looks a little bit more crowded compared to 2000 network. Of course, a lot of people left the study, so that's very typical of any type of human subject evaluation, where human subjects or human participants are involved in the research. So attrition is always there. Still, even after you discount for the attrition rate, you'll still see those interesting patterns emerge even after 5 years. Now I'll go even deeper in this network. So we know now the relationships that the nodes are connected through some type of relationships, whether they're spouse, friends, family members, siblings, etc. So we'll see what type of relationships were coded in this network. Plus the nodes here, circle and square. So circle representing females, square representing males, and then the colors. The brighter the colors are, the happier those individuals reported their status or their state being on that day, on that survey form and that Likert scale. And then the bluer the nodes are, the gloomier or the sad they feel on that day, right? So that is the color coding here. Now, when you look at these two networks, right, even though they are 5 years apart, you will see something interesting that let me try and zoom in and see if that helps. Now, here you will notice that there is some type of a clustering going on. And of course, the researchers didn't do anything, no manipulation in the network, no refinement, no filtering. This is the raw network that they obtained. And this network actually shows that the state or the mental state, emotional state of individuals are highly correlated. So people who were feeling sad or gloomier tend to have a similar reaction from their connected individuals, right? And people who were bright and happy mood, happy emotions, they tend to have a similar reaction from their neighbors, right? So this is also known as segregation of behaviors in the networks. Now, one thing that the researchers also tried to understand whether this is actually a contagion or just happened to be a correlation, meaning if I'm happy, am I making my neighbors happier, or is that just a property that, yes, there is a just good correlation between people who are together there. If they are happy, they are together. They're sad, they're together. So there is a correlation, not a causation. So me being happier does not make sure that others are happy. Just both of us are happy together. Now, that was one of the concerns of the study. However, the researchers also looked at various things to try to address that concern. Increasing in the probability of your happiness, ego, again, ego alter, right? Ego happiness, if alter is happy. If your friends are happy, then how likely are you going to be happy? So just by looking at this network, they found that people who are one hop away, like the distance from the altar, if it is just one hop away, then they have the strongest impact on your happiness, right? So if your friends or direct connections, your neighbors, they are happy, then you will be happier. The chances are that you will be happier. If they are two hops away, then the probability decreases. Three hops, four hops, then kind of flat lines after that. So it's probably better to keep your friends happier, right? So that's probably the conclusion here. So happy friends make you happy. Um, the other experiment that they did was, does the number make any difference? Like how many happy friends you need to increase your happiness, right? So they start with zero. I mean, zero is the baseline. So, okay, after one, two, three, and you can see that, it kind of tapers off. So no more increase in or no more noticeable increase in happiness is observed after three number of alters, meaning the maximum happiness can be obtained if you have three happy neighbors. So you don't have to please everyone. That's the conclusion here. You just need a few happy friends and then you're all set, right? Um, yeah. Now, the other experiment that they did was, if we start to characterize the relationship types and then see which relationship type has the most impact on ego's happiness, right? Again, ego alter network. So as you remember that the survey had asked to define your relationship. So it could be, so the respondents of the survey mentioned either as a nearby friend, so they're visiting a nearby friend, or they're visiting a distant friend, or it's a nearby mutual friend, nearby alter perceived. So alter thought that they are the friend, but ego may not have thought that, right? Again, directed undirected networks. Co-resident spouse or non-co-resident spouse, nearby siblings, distant sibling, next door neighbor, same block neighbor, so on, right? So if you look at this chart carefully for different relationship types, of course, there is a differential impact in happiness, meaning not all the relationship types have the same impact on your happiness. Some have higher, some have lower. The highest one that was reported was with nearby mutual friend. So the idea is, um, two people having a mutual friend. So if that mutual friend is happy, then the chances are, you are happier. Right? And then next one after that was next door neighbor. So if your next door neighbor is happy, then they have a higher impact on your happiness, on the ego's happiness. Right? And then there are other relationships, nearby friend, and I think it's after that probably nearby alter perceived friend, and then maybe nearby sibling, um, co-resident spouse, non-co-resident spouse, and so on. Right? Yeah. All right. So this is also interesting because not only happiness spreads, it depends, who you're connected to, how many neighbors are happy, uh, to what degree or hops you want your networks to be happier, so that has a direct impact on your state, emotional state, right? So this paper is also available through this link. So if you're interested, you can download this paper and read up about it. The same set of researchers conducted few more studies on how smoking spreads, and also through that behavior, through that study, how smoking behavior can be influenced. So interventions for smoking cessation and so on. Spread of obesity. So that's also one of the virtues that they studied, how networks can influence your dietary habits, and etc. Right? All are very, very interesting studies which show in a very fun manner, interesting manner, the roles of network in our individual behaviors, choices, decision making, which is often used for the social good, but adversaries also use that to exploit, to uh, exploit your cognitive capacities, right? To influence your behaviors and beliefs, and even advertisement and marketing campaigns leverage some of these concepts, right? Okay. Any questions or thoughts? Okay. All right. Let's see. I think I heard something on like. Oh, okay. Okay. Good. All right. So we looked at um, sociometry or the social sciences, how they understand, how they look at social networks, what are their terms, terminologies, but not in depth, of course. I mean, two slides cannot do justice for the entire social sciences discipline, how they understand social networks. There are books and books and books on social network analysis from social scientists. So if you're interested, I would definitely suggest you to look up some of the literature from social sciences. But since you're part of computer information science, we will be sticking with the terminology that is more prevalent in computers and information science discipline, right? We then also looked at how networks influence our behaviors, decisions, choices. We looked at some examples. Now we'll see how social networks can also be applied in something called bibliometrics. Bibliometrics is a separate study where we try to understand the nature of research articles and how influential they are, who are influential authors, researchers. So that whole area is called bibliometrics. In fact, many conferences, journals now provide statistics, mention statistics on their websites, suggesting how important or how top tier, how competitive this conference or this journal is based on things like citation score or bibliometrics scores and so on. So we'll be discussing some of those concepts here. That will tell you, how social networks can be leveraged even in such type of topics, such type of discipline, right? Because you can imagine there are quite a striking similarity between bibliometrics and social networks. Bibliometrics is nothing but a network of researchers through their citations, right? So when you write a paper, then you have something called a reference section. You're citing someone else's work to build your argument or evidence towards your research discoveries. So such type of citations can be considered as relationships between papers, between manuscripts. So if a paper A cites paper B, then you can connect those two papers using the citation relationship. You can then further abstract it to authors. If the author of manuscript A cites manuscript B, which is written by author B, then author A and author B can be connected, right? So those are the kind of the nature of these networks. And you may have already guessed that such a network would be a directed network. This is also very similar to a web network where you have web pages or websites connecting to each other. So if a website A hyperlinks to website B, then you have an edge going from A to B, but not necessarily vice versa from B to A. Okay. All right. Now, if we start extending those relationships of citations between two papers or manuscripts, we can see that if two papers are cited by the same paper, then they could be related, right? Similarly, if two papers cite the same paper, they can also be related. So we will take a deeper look at these two statements in the next few slides, but in fact they have their own terminology, which is called co-citation and bibliographic coupling. So if two papers are cited by the same paper, that is co-citation, right? Paper A and paper B both are cited by the same paper C. Then A and B are co-cited by C. Which is basically if you go and read a paper, at the end you have a references section. So all the references that are cited by this study can be considered as co-cited, right? Because this manuscript has cited all those papers. So that's a co-citation network. The other one, the second statement, is called bibliographic coupling. And bibliographic coupling defines it creates a network where two papers cite the same paper. So manuscript A and manuscript B both have cited the same study, right? So in that case, we end up with a bibliographic coupling network. And in both cases, these relationships tell us about the nature of these studies, which is if two papers are cited by the same paper, like all the references, they probably are, in the same field of research, same discipline, or even if they are in different disciplines, they may be attempting to solve the same problem from different perspectives or different approaches. If two papers cite the same paper, then also that means that these two papers are kind of related because they have same or similar papers in their citation indices, suggesting that they are all working in the same area of research or same topical areas. And this is very powerful concept because even without reading the papers or without doing any content analysis, just by looking at this network, you can tell which studies are related, which studies are not that much related, right? All right. Now we'll start exploring these two networks more deeply, so that way you understand what these networks are and what can be discovered from these networks, what we can infer. Okay, co-citation network. Again, the idea is if articles I and J are both cited by the article K, then they are related in some ways, either topically or a research problem is the same, or they adopt the same methodology to solve same problems. right? So this is how a co-citation network would look like. Again, we are trying to govern how similar I and J are depending on how many papers co-cite them. So the more such Ks or more such papers exist on the right that cite both I and J together, the more similar I and J are, right? In fact, this can be actually mathematically defined using um, the formulas or the mathematical representations that we have looked at before. So if you consider the citation matrix, which is nothing but your adjacency matrix, L, right? Each cell of the matrix is defined as follows, where Lij or the paper article I cites article J, then it is 1, otherwise 0, right? Very similar to your adjacency matrix. If node I or a person individual I connects to individual J, then you go to that cell in the matrix and then you put a 1. If they're not connected, you put a 0, right? So in that case, you start with this adjacency matrix of ones and zeros depending on who cites whom, right? Only in this case that this Lij is going to be a directed network, right? Because this co-citation is a directed network. So you will find that Lij is a non-symmetric, or it's a asymmetric matrix. Okay. So Lij will be asymmetric because this is a directed network. Now co-citation, we can denote that by Cij, meaning how similar how similar two articles I and J are, depending on how many papers have co-cited them, right? So we calculate that by doing this matrix multiplication, where we know that Lij is your adjacency matrix. So we add up the product of Lki and Lkj. Again, if you understand this, then it'll be easier to follow. So I'll try to, break this apart and then we'll go through each term so that we'll understand this formula. So Cij is basically nothing but how similar two papers I and J are, depending on how many K cite them, how many articles cite both of them, right? And to do that, we need to know whether there is an edge between K and I, and if there is an edge between K and J. Now, if you look at the adjacency matrix, Lij is the edge between I to J. So instead of Ij, you're looking at Ki and Kj. So you can say Lki and Lkj will be those edges, right? So if Lki and Lkj exist, meaning there are these edges, then we just do a product, right? So Lki times Lkj will tell us whether they both I and J papers are cited by K. Because if either one of them is 0, then the product will be 0. If both of them are 1, meaning both of these edges exist, if these edges exist, then the product will be 1. Right? So Lki times Lkj will be 1 if both these edges exist. And if they exist, then we want to do the same thing for all possible Ks. So let's say if there are n nodes or n papers in the network, then we iterate it from k equals 1 to n. So for all those k where node k's where there is an edge from k to I as well as an edge from k to j, then this will be 1, and then we keep adding that, right? So ultimately you will see a number here, a whole number here, positive, which will tell us how many papers have cited both I and J. So that's basically a count on total number of papers that have cited both I and J. The higher that number or the closer that number to N is, that means it is these two papers are that much more similar, right? So according to co-citation phenomena, we can then govern that these two papers are highly similar if that sum is close to N. Okay. Now we already know that the matrix L is asymmetric because it's a directed graph, right? So for a directed graph, we know that this matrix is asymmetric, meaning the above diagonal entries may not be same as the lower diagonal entries, because it's not necessary that if k cites I, then I will also cite the article k back. In fact, it is not possible. This is always a temporal graph where an article that cites another article will be published after the article that they have cited, right? So in this case, this is always a directed graph. It cannot be bidirectional. So this is always asymmetric matrix. So L is asymmetric, so this will be no. Now the question is, knowing that fact, can you tell us if C, the matrix C, co-citation, is symmetric or not? Right? So we know that L is not symmetric, but is C symmetric? Anyone? What do you guys think? Will C be symmetric or asymmetric? Let's see. Okay, and says, I think C will be symmetric. Okay, anyone else? There are only two choices, so C can be either symmetric or asymmetric. So according to probability, you are going to be 50% correct. Okay. Also symmetric. Okay. And knowing the fact that L is asymmetric, right? So the matrix L is asymmetric. We just want to know whether Cij is going to be symmetric. And if you look carefully at this formula, you will be able to know whether it is symmetric or not, because we are trying to find how similar paper I and J are. So for paper I and J to be similar, this is the formula to know. And symmetricity is defined as, there is no difference between I to J and J to I. If I to J is same as J to I, meaning if Cij is same as Cji, then it is symmetric, right? So you can actually do this math very briefly or quickly in your head. If you change or swap I with J and J with I in this lower subscript, what changes will it impact here, right? Let's see. Instead of Cij, if we wanted to write this as Cji, then the only difference you're going to observe here is instead of I, you put J, and instead of J, you put I. So this will become Lkj times Lki. Now we know that product of two things is always symmetric, right? So it doesn't matter if you multiply 2 with 3 or 3 with 2, the outcome will still be 6. So if you consider Cij or Cji, it's not going to make any difference, right? So Lki times Lkj or Lkj times Lki, they're both same. So in that case, and John, James, you're absolutely correct. C is symmetric. Even though L is asymmetric, C is symmetric. So in fact, we did a little bit of math proof here. So just replace I with J and J with I. Yeah. And this is all at 7 p.m. in the night. So kudos to you guys. You guys had, I think, enough share of your coffee for the day. So yeah, this is absolutely correct. So you can actually do this math and you can prove that C is a symmetric matrix. All right. So we looked at co-citation, and the other phenomena was bibliographic coupling, which is very similar to co-citation. The only difference is you just reverse the relationship. Instead of K citing INJ, now you have two papers, INJ, citing the same article K, right? And the more such articles that these two papers cite, the more similar they are, right? So that is called bibliographic coupling. So we use the same adjacency matrix to define this relationship, just like we did here. So an article is connected with the other if there is an edge, and then Lij in that case will be 1, otherwise it will be 0. Now, to know how similar or what's the bibliographic coupling between two articles I and J, notice how we changed this product. Now we are interested in whether I cites K and J also cites K, right? So here you will see Lik and Ljk. So the product between Lik and Ljk, because we are establishing the edge from I to K, similarly from J to K. And more such K exist, the higher this sum will become, right? So if both of them are 1, then 1 times 1 is 1. Otherwise, if any of these edge don't exist, it will be a 0. So the sum or that number, that product will be 0. So as close as this sum is to n, the more similar those I and j are, or basically Bij will be higher. Okay? They will be more related. The same question I think you can now easily answer. We know that the matrix L is asymmetric because it is a directed graph, but Bij will be symmetric, right? Because again, the product is commutative. So Lik, Ljk same as Ljk times Lik. So B is also symmetric. Just like C was symmetric, B is symmetric too. Okay. All right, any questions? Okay. So we also saw how social networks can be applied to bibliometrics to understand similarities between two papers based on co-citation and bibliographic coupling relationships. In fact, we skipped a whole lot of bibliometrics that also leverage social network analysis, where you're trying to identify who are the most influential research papers or influential authors, which leverage the same concepts of centrality. So higher citations mean more popular. So you can just count the degree, or you can do a more advanced analysis using eigenvector centrality, meaning a paper is that much more popular or that much more prestigious if more prestigious papers cite it, right? So the very concept of eigenvector centrality that is applied. So that's how journals get their citation scores, authors get their H index. So when you start searching about papers or authors, you will always, you may run into these scores, H index or cite score, citation score, all these metrics kind of measure how important or how popular, how competitive a journal is. So how many citations they get. Okay. All right. Now we have just few more. I think this is probably the last or second to the last slide. Here I want to leave you guys with some more advanced concepts on social networks. Of course, even 2 lectures on graph theory are not sufficient, but I don't want to belabor graph theory that much because we have a lot of ground to cover in terms of hands-on, in terms of data collection, analysis. So there are so many more advanced concepts and interesting concepts that are that much more applicable or pertinent to daily lives, social settings, social observations. So some of those concepts, such as hypergraph, have started to make into literature, research studies, where so far, since we have looked at only dyadic relationships, meaning two individuals connected with a edge, but you can think of social settings where these relationships could stretch beyond just two individuals, right? So a team of three, four, multiple members, right? So such type of relationships are considered as supra-dyadic or beyond dyadic, right? Relationships. And regular social networks or graphs that we have seen, they are not adequate to represent such relationships, such complex settings. So for that, there is a new line of or a new area of graph theory, which is called hypergraph. And hypergraphs define parallel concepts. We will take a look in the next slide for degree, for clustering coefficient, etc., and clustering the networks, where multiple individuals could be involved in such relationships, right? So you can think in terms of, let's say you're doing a group project, and how would a single edge connect a group of four or five or even three individuals, right? So the best way you can do that is by creating three edges between three individuals, but still it will govern only pairwise relationships, that A with B, B with C, C with A. But if all three are working together, then you cannot have, kind of a regular graph representing that relationship between three individuals, right? In more complex settings like mobs or crowds, large groups, social movements, protests, where individual or pair-wise relationships are definitely not adequate to represent the whole dynamics, the whole complex situation, complex networks, then you definitely need hypergraphs for that, right? If you want to do much more complex analysis. The way to represent hypergraph is not same as the graphs. Here, instead of edges, you consider sets, where a set governs the individuals or the nodes that are in relationship. So you can see in this case, you have a set called E1. We can consider this edge 1, which has three individuals in relationship, V1, V2, V3. You certainly can have an edge with just two individuals, like E2, where you have V2 and V3. E3 is another edge that connects V3, V5, V6, right? And then you can also consider another type of relationship where the individual V4 is in this relationship, right? So you can also have one individual in the edge set, right? V7 is not connected, so that's a separate isolated node, right? So these are hypergraph representations. So you have a set of vertices and a set of edges. Edges are themselves sets of vertices. So this tells us, how a hypergraph can exist. Interesting thing here, if you notice that V3 is part of three different relationships, right? One with V1, V2, V3, another one with just with V2, and then the third with V5 and V6, right? Yeah. Now, given this information, you can start to think about parallel concepts. Like for hypergraphs, you will have an incident. You can create an incidence matrix, similarly, just like we did previously. So here you have these edges and vertices. You can consider degree, centrality, clustering coefficient, but those are much complicated formulas. So I didn't put them here, but those parallel concepts exist. And if you're interested, I can share more literature on that where such definitions or formulas are provided, so you can understand mathematically how they're computed. But if you were to calculate degree, which is the simplest way of a vertex, you can clearly see for vertex, let's say V1, how many edges or how many relationships V1 is a part of, right? So only one. V1, you can see that it's a part of edge 1, only one relationship. So here we have degree of V1 as 1, right? But if you were to calculate degree of V1 using the regular graphs, then you would see that V1 is connected with V2 as well as V3. So in those cases, the degree would become 2 for V1. But since now we are considering that all three, V1, V2, V3, are part of just one relationship, hence the degree of V1 is just 1. There's only one edge, right? One relationship. For V2, again, the same thing. V2 is part of this relationship, right? So we are not going to say V2's degree is 2 because it's part of, these other relationships, only V2 and V3, right? V3, on the other hand, is part of multiple relationships, E1, E2, as well as E3, right? So there will be the degree for V3 is 3. For V6, for V5, both these nodes, the degree will be 1, right? Similarly, for V4, even here, the degree will be 1 because there is only one relationship that V4 is engaged in, right? So again, here you're counting the number of relationships that you're engaged in, degree, and then centrality can then be calculated based on a ratio of how many possible relationships can exist and how many relationships are actually there. So that will give you centrality, and clustering coefficient will then tell you how many triadic closures could be there, open relationships are there. So how many open triads were divided by the closed triads. But those formulas are much complicated, so I will put them here. If you're interested, I can share more literature on that. Right. I just wanted to leave you this with this concept. It's not that we are going to use hypergraphs in our course because it will be definitely out of the scope of senior level course or even first year graduate level course. But these concepts are now becoming widely popular in social computing. So if you are exploring your career or thinking about doing research in social computing, then these concepts will come in handy, right? Okay. All right. Any questions or thoughts so far? Okay, good to know. All right. Well, what we can do, good. What we can do now is, this is all what I had planned for graph theory. So I'm sure you guys are also kind of getting tired with all the math and all the concepts, and you're getting restless to try these concepts out. So what we will do is we will kind of, take a different turn now. Instead of looking at concepts and theory, we will start looking at some more applications of these, starting from data collection first, because so far I'm sure you may have seen a lot of data from social media platforms. When you go to their websites, you see so many posts, so many contacts, individuals are posting, people are liking. So that is one form of data observation. The other form of data observation is when you write a computer program that can fetch all the data for you. So if you're interested in certain event, let's say Apple had an event, I think yesterday or the day before, probably. They released a bunch of products and you're interested in, okay, what people are saying about these products on social media platforms, maybe Twitter X or Facebook or Instagram. Are people talking about these products in a positive way, or do they like it? What features they like? So you can collect all that information and do some summarization, emotion analysis or sentiment analysis, and that can give you some interesting insights into what people are thinking about these products. And I'm just taking this as an example, but you can probably stretch your imagination into any type of events or any type of topics you're interested in, right? So We will do that. So from next class onwards, we'll start looking into data collection first, and then data visualization, network visualization, analysis. So all the concepts that we have discussed in the last this lecture and the last one will be very helpful. So those visualization analysis software will do most of the work for you, but they will leave the interpretation to you. Meaning, when they report this is the degree centrality value, then you have to remember your fundamentals. What does it mean? Degree centrality of 1 or degree centrality of 0.5. Similarly, if you run clustering coefficient scores, then if you get an average clustering coefficient of 0.8, then what does that mean? So you can refer back to these concepts that we covered in the last class and today to know all these things, right? How to interpret those scores or those measures, right? So that will be sort of the roadmap for next few lectures. So we'll dedicate a lot of time on data collection, data analysis, data visualization, and then also something called content analysis, where not just the network, as we have seen, social media platforms are rich with content, both text as well as multimedia content, images, videos. So we'll be looking at all those variety of content analysis techniques. Right, and having familiarity with some programming language will be helpful, but if you don't, that's not a deal breaker. We will post enough scripts, etc., on our Blackboard page so that you can just take those scripts, run those, and then you don't have to worry about how to program or how to do this or that. But again, those will be highly hands-on lectures. Um, so we will adapt to the speed of the class. And if you have any questions, if you feel lost at any point, feel free to stop the lecture or ask the instructors. So what we'll be doing is I'll be bringing a lot of guest lectures for next several classes where they will go over specific data collection from various platforms, and then data analysis, visualization, content analysis, right? Okay, but we are not going to stop the lecture tonight so early. I also have planned one more thing, which is assignment one. So I'm not sure if you have seen that. Maybe some of you did. Assignment one has been released. So let me see if I have it handy here. Oh, there you go. Okay. So this is released, and the way to find this, yeah, yes, 100 points, absolutely. But again, this assignment is entirely upon the last lecture and today, right? So the things that we have discussed in the last two lectures are contained in this assignment, right? So this will make sure that you revise the lecture, go through the recording. And again, this is not a tough assignment, as if you have followed the lecture, it will be very straightforward. There are 10 problems here, as you can see, and you're not expected to write a lot on each of these problems, as brief as you can be. That is much appreciated. Prepare your responses to individual questions and combine them all in one Word file or whatever your preferred editing software is, but upload as a PDF file, right? Often I've seen people upload Word documents, and when it is uploaded on the browsers, the formatting gets messed up. So if you can convert that to PDF, upload it, that will retain all your formattings. Okay. There's no word limit for this assignment, but again, try to be as brief as you can. If you can, respond to that question in 20 words, 25 words, good enough. We are just looking for your conceptual understanding, that you understand what those concepts are, not as much as how much you can talk about that concept. Okay. Mm, yeah, and this is again available on course Blackboard page. Um, just to give you a quick look, let's see if I can show where it is located. So when you guys open Blackboard, you will notice that the assignment is a separate folder right under lecture materials. So if you expand that, you should see assignment 1. And I believe when you click on assignment 1, it might show a separate um, interface for you. But there should be a place where you can, submit your assignment. I believe should be able to see that somewhere. Right, or I can see if I switch to the student preview and see if that helps us. Assignments. Okay. So when you click on instructions and then go to the submission section, then you can drag and drop your file here. And I believe once you upload your file, then the submit button should activate and then you should be able to submit. Right. Good. All right. A couple of other instructions. This is an individual assignment, so attempt it individually. Make sure that your assignments or your responses are not shared with someone else. It will affect not just their points, but also your points. So keep them to yourselves. Your assignment is due 2 weeks from now. Although I'm sure you will not need that much time to respond or to prepare your responses to these assignment, but still you have 2 weeks. And in those 2 weeks, if you have any questions, again, feel free to email me and ask those questions. But I think this should be straightforward. This is directly right out of the lecture notes or lecture slides. So if you're following the lecture, should be straightforward. Right. Okay. Let's see. Okay. Let's see if you have any questions. Exemplarity. Yes, that's fine. Again, while responding to these, as you can see that there are some, I've asked for some examples. You can, yes, use the examples that I have given in the lectures. If you have your own examples, feel free to share them. So both of them are fine. Yeah. Okay. All right. Well, if you don't have any other questions, then we can wrap up today's lecture now. But if you have questions, we can stay a little bit longer and then I would be happy to take your questions. It could be anything from this assignment or anything from the lecture or the next few lectures or the course in general. Okay. One thing I would also remind everyone, we will have after this assignment just one more assignment. And after that, then we will move to our course project. And the course project, typically I do in 3 phases. The first phase is typically a course proposal or a project proposal. The second phase will be sort of an intermediate project report. And the final phase will be your final project report. And sometimes, if time permits, we can also do presentation. Right. So those are the 3 phases of the project. Other than that, 2 assignments, and that's it. So we will have these 5 deliverables for the whole course. We don't have any exams, midterms, or finals. So we will be just concentrating on these 5 deliverables. And yeah. Right. Okay. All right. Any other questions, thoughts? Oh, all right. Well, in that case, yep. I wish you all a good weekend, and I'll see you guys next week. All right. Thank you. Thank you all for attending, and see you guys next week. Take care.